Please welcome to the stage Dr. Paul Weiss, UC Presidential Chair and Distinguished Professor at UCLA.
Well, this talk follows nicely, actually, after my friends Yuri, Deji, and Roger. So what we try to understand in the fundamental science part of my laboratory is how and why nature uses such poorly conducting molecules to move charge around. So when we want to move charge, we use a metal wire. Enzymes could perfectly well fabricate wires, but they don't. We also sometimes use conjugated aromatic molecules, like in organic LEDs, and enzymes, once again, could synthesize those, but they don't. Let's go on. So we heard a little bit about this both yesterday and today. Right? Our brain uses about 12 watts of power, 2 million times less than the leading supercomputer. We have 100 trillion connections in our brain. It functions quite differently than a computer does. We have 100 different interpenetrating chemical channels for signaling. There was a talk about that earlier, in addition to voltages. The voltages that are used are much lower. We usually use as an energy scale the thermal energy, the energy available from the air around us or in a liquid. That's about 100 times lower than the voltages that we use in our electronic devices. And so we would like to be able to understand what we could do that would enable us to go down to those lower voltages, lower energy usage, and we'll talk a little bit about that energy efficiency. So this should be spinning. There we go. Nope, go back. It started. That didn't click back. There we go. So my colleague, the late Paul Boyer, figured out how these motors worked that each of us has in us. So using one molecule of ATP, the chemical fuel in us, they rotate 120 degrees and pump a proton across a membrane. And we actually use more than 50 kilograms of ATP each day. So we don't carry around a bag of it like we carry batteries for our laptop or our cell phone. It's that fuel is used over and over and over by recycling. Okay? Similarly, this motor can convert chemical fuel to motion with greater than 99% efficiency. In fact, it's so efficient you can push the proton back through the membrane and get the fuel back. So think of how we do recycling and how poorly that works for sustainability. We've heard some of the talks about that, right? If we take a plastic bottle, we have to separate the pieces. We put a tremendous amount of energy to go back, not quite to the starting products. In fact, we usually make a park bench or a blanket or something else. We don't really get the molecules back, but it costs us a lot to do that recycling. Imagine if our fuels, or the molecules we used in motors, for instance, could do something like we see in biology. So one other sort of energy scale to think about is in our axons. In our nerves, we're really going to much smaller scales than Roger Penrose talked about a few minutes ago, at about 2.5 times thermal energy, right? What's called an action potential across a membrane, accelerates information transfer over centimeters. In fact, in a single cell from our spine all the way down to our feet. Okay? So very small amount of energy, very large effect. How do we do that? So I feel like we're missing something, and that's what we're exploring in our laboratory. My laboratory is best known for exploring the ultimate limits of miniaturization, the smallest switches and motors in the world. We're particularly interested in these low energy effects. So a visible photon, for instance, is about 100 times thermal energy. So we don't want to use visible photons. We don't want to use high energy probes. And so really another talk is the kind of microscopes that we build that get atomic resolution and can measure these kinds of processes. So one of the things we look at is how spin might be conserved in chiral biomolecules. In fact, the microtubules we heard about in Roger Penrose's talk are chiral, but so is DNA, so are many peptides. In my laboratory, what we try to do is recapitulate natural systems and synthetic ones so we know where every atom is. I have kind of OCD about that. And we can go from quantum mechanics to engineering and experiment theory and simulation. We have some advantages here in that when you go to lower energies, the wavelengths are longer. And so that may help explain these processes. The other aspect is polarizability. So as in the action potentials, where a small potential across a membrane has a large and long-range effect, we can push electrons into either conducting channels or even into these chiral channels that may then help us conserve spin. And one recent example that came out, I couldn't get into the animation, the details of this, but there are a couple of species of bacteria that produce energy, called Geobacter and Schwannella. The term for them is electrogenic. When we finally took these tails that you see sort of wiggling around here and got their atomically resolved structures, we found that while those are, conductors, the molecules that are responsible for conduction are not even in contact with each other. And so those longer wavelengths and polarizability, we think, may help explain the conductivity in those what are called pili, the wires that we have yet to understand. And so what we've done is say, well, look, the way we make a polarizable molecule is we have what are called multiple bonds, like in conjugated molecules. And so trying to think in the way that nature uses these effects, what could we do? So we took, this isn't maybe the most explanatory slide, but we took molecules that are a cage. There are 12 atoms in the cage, and they have multiple, all interconnected bonds, so they're very highly polarizable. We put a single layer of those on a surface, and as you've heard about many 2D materials over the last 2 days, we used a single layer of graphene over the top to serve as our top contact or our top electrode. Okay? And then we could apply a small potential between the two to push electrons into and out of the bond of the substrate. One of the reasons we use these overlayers is if we made a chemical bond to the molecules, we change their electronic structure, and that would disrupt the polarizability and disrupt the bonding of the molecules. So this is kind of a fair way to test one family of molecules against another. And when we did that, what we were able to do is by pushing electrons into and out of the bond, we could change the thermal conductivity, how heat is conducted through those layers. So when people try to make thermal switches, if they got 15% effect for the difference between on and off, they would be celebrating. Typically, those switches involve large molecular motions or phase transitions or polymer reorganization, and so they're very slow, minutes or hours. Well, electrons move fast. In our measurements, we've measured up to or I should say down to 100 nanoseconds, but in fact, we think they're much faster than that. So in our demonstration, we're at least 8 orders of magnitude faster, 100 times bigger effect. We got a 1,300% effect just in the very first molecules we tried, and at least an order of magnitude thinner. So we have yet to optimize. If, for the material scientists, chemists, and physicists, we can also use twistronics on top and launch chiral heat waves coming through these molecules. So we think there are many, many other opportunities where we can take what nature is doing, take that perspective, and then learn to use lower power, learn to give greater control, and learn to add greater function to the systems that we study and that we're able to fabricate and put in devices. Thank you very much.